Hello guys, welcome to the second part of the discussion on moving loads. So if you missed the first part of this discussion, so I have the link posted in the description below. And then we have here example number 3. We have a three-wheeled truck. So we have a truck and trailer combination crossing a 12-meter span, has axle loads of 10, 20, and 30 kilonewton, separated respectively by distances of 3 and 5 meters. Compute the maximum moment and maximum shear developed in the span. So we have here a 12-meter span. Let's say that's bridge. Okay. Then we have axle load of 10 kilonewton, 20 kilonewton, and 30 kilonewton. And they are separated by a distance of 3 meters. Or this one is 3. And 5 meters respectively. So we have 5 meters here. Okay? So we compute for the resultant. Now our resultant here is the summation of all the axle load. Let's say we have the resultant at this point. This is only an assumption. Okay, so we have the resultant which is equal to 10 plus 20 plus 30. We have 60 kilonewton. The next is the location of the resultant. So let's say we refer from 30 kilonewton. Let's say that's our x. Okay. So therefore, the distance of 10 from 30 kilonewton is equal to 8 meters, correct? So we have this distance from 10 to 30, we have 8 meters. And the distance between 60 and 10, this distance here is equivalent to what? We have 8 minus x, correct? And the distance between 20 kilonewton and the resultant 60 kilonewton is this distance here, 5 minus x. No? This one is 5 minus x. The distance between 20 and 60 kilonewton. Since 5 meter is the distance between 30 and 20, so we minus x, okay, this distance, and that would give us 5 minus x. Okay, so we balanced, or we locate the location of 60 from 30, then we have 60 times x equals to, basically this is just Varignon's theorem, okay, equals to 10 times 8, correct, plus 20 times 5. Okay, that's a distance of 20 from 30 kilonewton. So we have the value of our x here, which is equal to 3 meters. So therefore, this distance here is 3 meters. And the distance between 60 and 20 is 5 minus 3. This one is 2 meters. And the distance between 60 and 10 is 8 minus x, or 8 minus 3. This gives us 5 meters. Okay? So since we have now the location of our resultant, so we can now compute for the maximum shear by positioning the load on the support. Okay, we just referred to the outside load, which is 10 kilonewton and 30 kilonewton. So we exclude 20 kilonewton here. Now we know that 30 kilonewton is the nearer load from 60 kilonewton compared to 10 kilonewton. Since we have 3 meters distance from 30 to 60 kilonewton, while 10 kilonewton is 5 meters away from 60 kilonewton. So 30 kilonewton is the nearer axle load. Okay, so we place 30 kilonewton on support B. Okay, so we have 30 kilonewton on support B. So we compute for the reaction at B, since that reaction at B is the maximum shear. So we have to sum up moment at A, okay, this equals to 0, and the counterclockwise rotations are positive. So we have RB times 12 minus 60, so we use the resultant instead of the load. Then the distance from A to 12 to 60 kilonewton is equivalent to 12 minus this distance of 30 from 60 kilonewton, which is 3. So 12 minus 3, this gives us 9 meters. Okay? So we have 60 times 9 equals to 0. So we have RB here, which is equal to 45 kilonewton. And this is our maximum shear. Okay, since we have now determined the maximum shear, let's proceed now to the determination of the maximum moment. Okay, now, in our first case, we placed the midspan between 10 kilonewton and 60 kilonewton on the center line. Okay, so basically, since we have 3 loads here, so therefore, we should have 3 cases. Okay, so let's try to solve first the maximum moment under the load 10 kilonewton by placing their midspan on the center line. Now, we know that the distance between 10 and 60 here is equal to 5 meters, correct? So therefore, from the center line to 10 kilonewton is 2.5 meter, and from the center line to 60 kilonewton is 2.5 meters as well. Okay? So in that case, we compute for the distance of 30 from the center line, because this might be outside of the beam, that the outmost load may fall away or may fall outside of our beam. Okay, let's check the distance of 30 kilonewton from the center line, and we have here 5 plus 2.5. So we have here 5. This distance here is 5 meters, correct? Plus this distance. Okay, how are you going to compute this distance? Now we know that we have 2 meters here, okay? The distance between 20 and 60 kilonewton. So therefore, we have remaining here, which is 0.5. This one is 0.5. So we have the distance is equal to 5.5 meters. Okay, since again, 20 kilonewton to 60 kilonewton is 2 meter distance. Okay, so therefore, since we have 2.5 from the center line to 60, so we have 2.5 minus 2, this would give us 0.5. So we have the distance between 30 to center line, which is equal to 5 plus 0.5, this is 5.5 meters, which is less than 6 meters, correct? Since we know that we have this distance here, which is 6 meters. And we can say then that 30 kilonewton is on the beam. Okay? Now we can say then that 30 kilonewton is inside the beam. So let's compute now for the reactions. Okay, so therefore we compute for RA here, since this is on the side of 10 kilonewton. So we sum up moment at B, this equals to 0, counterclockwise positive. So we have here RA times 12 meters, that is the distance from B. Okay, this is negative since the rotation is clockwise, plus 60 kilonewton times from B, the distance of 60 kilonewton. Okay, this distance here is 6 minus 2.5. Okay, and this is 3.5 meters. So we have 3.5 meters. And this equals to 0. So our RA here is 17.5 kilonewton. So we have RA, which is 17.5 kilonewton. Now, to compute for the moment, the maximum moment for case number 1, so we just cut at this point. So we have here, now we compute for the distance, and the distance is 6 minus 2.5, and this is 3.5 as well. So we have 17.5 times 3.5. This will give us 61.25 kilonewton meters. Okay? So this is the maximum moment for case 1. Now for case number 2, we place the midspan between 20 kilonewton and 60 kilonewton on the center line. Okay? So this is to compute for the maximum moment under the load 20 kilonewton. So in that case, since we know that 26 to 60 kilonewton is 2 meters, correct? So therefore, the distance from the center line to 20 kilonewton is 1, and from the center line to 60 kilonewton is 1 as well. So in this case, we compute for the reaction at A, because A here is on the side of 20 kilonewton. So we sum up moment at B. This equals to 0, counterclockwise, positive. So we have here negative RA times 12. Then we have plus 10 plus 60 times the distance of 60 to B. We have here 6 minus 1, because this distance here is 6 meters and we have 1 meter distance here. So we have 6 minus 1, this would give us 5 meter distance. So we have 60 times 5 is equals to 0. So we have RA here, which is equal to 25 kilonewton. So we have RA, which is equal to 25 kilonewton. So we will cut on 20 kilonewton. So we cut at this point. Now we compute for the moment by cutting at this point, okay, at 20 kilonewton load. So we would have this load diagram here. We have RA, which is 25 kilonewton. That's our RA. But we have 10 kilonewton load shown, okay, since we cut at 20 kilonewton. So 10 kilonewton here will be included in our cut section. So we have our moment. Let's say it's our moment 2, or that's in case number 2. And we have the distance of A to the section 2. Okay, this distance, which is equal to 6 meters, correct? Since we have 5 meters. Okay, since from the center line to support A, we have 6 meter. Okay, but we have 1 meter distance from CL, or center line, to 20 kilonewton. So therefore, we have 6 minus 1, and that would give us 5 meters. This one is 5 meters. But we need to determine the distance of moment 2 from 10 kilonewton load, since we have 3 meters distance from 20 to 10. So therefore, the distance here is 3 meters. Okay? So then we can sum up moment at 2 is equal to 0, counterclockwise positive. We have here negative 25 times 5 plus 10 times 3. Then plus M2 is equal to 0. So we have our moment 2 here, which is equal to 95 kilonewton meter. Okay, so this is our maximum moment for case number 2. Now for case number 3, we place the midspan between 30 and 60 kilonewton on the center line of our beam. Now we know that the distance between 60 kilonewton and 30 kilonewton here is 3 meters, correct? So therefore, we have from the center line to 30 kilonewton is 1.5, and center line to 60 kilonewton is 1.5 meters as well. Okay, now let's check if our 10 kilonewton load here is still within the beam. Okay, so we add, since we know that the distance between the 10 kilonewton load to 60 kilonewton is 5 meters, correct? So we add 5 meters plus 1.5 meter. So therefore, the distance between the center line to the 10 kilonewton load here is 6.5. However, we only have a 6 meter length here. So we can say then that 10 kilonewton load here falls outside of our beam. So we have our 10 kilonewton here on this way, since we have excess of 0.5. So therefore, we can say then that our 10 kilonewton has been eliminated in our load diagram. So we only have 20 kilonewton and 30 kilonewton on the beam. So there are changes in our computations. Okay, so we have different value for resultant, since again we have only two loads remaining, and that is 20 kilonewton and 30 kilonewton. So we have to apply the concept of a two-wheeled vehicle. Okay, since again we have only 20 and 30 kilonewton. And that brings us to case number 4, in which we only have 20 kilonewton load and 30 kilonewton load. So therefore, we have our new resultant, and the resultant here is 50 kilonewton. And we determine the location of our resultant from 30. Okay, let's say this is our x, and let's say this is our, now we have known that the distance between 20 and 30 kilonewton is 5 meters, correct, from the given. So we have here 5 minus x. So by Varignon's theorem, so we have 50 times x equals to 20 times 5. This will give us x equals to 2 meters. Okay, so we have 2 meter distance from the resultant to the 30 kilonewton. And we have 5 minus x, or 3 meter distance from 50 to 20 kilonewton. So we can now compute our maximum moment by placing the distance or the midspan between 50 and 30 on the center line. Now we know that resultant to 30 kilonewton is 2 meters, so therefore we have 1 meter distance here from the center line to the resultant, and 1 meter distance from the resultant to the 30 kilonewton load. Okay, so we have here to now we have to compute for the reaction. Now in this case, we compute for the reaction at B, since reaction at B here is on the side of our 30 kilonewton. Okay, so we have here to we have now to sum up moment at A is equal to 0, then counterclockwise positive. So we have here RB times 12 minus 50 times, now this distance here is 6 meters, correct? So therefore we have the distance of the resultant from A, which is equal to 6 minus 1, which is 5 meters. So we have 5 meters here, and this equals to 0. So we have RB, which is equal to 20.833 kilonewton. Okay, so we can now compute the moment by cutting at this point, okay, at 30 kilonewton. So let's say that's our we have this cut section in which this is our RB. RB is 20.833, and we have our moment. Let's say it's our moment 4, because this is case number 4. And the distance from 30 to support B is 6 minus 1. We have 5 meters. Okay, so we have here 5 meters. So we have summation of moment 4. This would give us M4. Summation at moment 4 is equal to 0, counterclockwise positive. So we have here negative M4 plus 20.833 times 5 equals to 0. So we have our moment 4, which is equal to 104.167 kilonewton meter. So this is the maximum moment for case number 4. Now, if you may ask, do we still need to compute for the maximum moment by placing the midspan between 20 kilonewton and 50 kilonewton on the center line? That was the procedure, correct? However, if we do that, there would be a possibility that the 10 kilonewton load will go back to the beam, yung 10 kilonewton na nasa outside ng ating beam. So, pwede siyang bumalik dito. Okay, so we go again to the previous procedure. So, uulit na naman tayo in that procedure. So, in that case, pwede nang hindi na natin yon gawin. So, we go directly with 30 kilonewton na lang. Okay? So, we have this case number 4. Now, to compute again, to determine the maximum moment, so we compare the moments that we have computed. Okay? For case number 1, this was our moment, which is 61.25 kilonewton. For case number 2, this was the computed moment, which is 95 kilonewton meter. Now, for case number 3, we have not computed moment. Now, for case number 4, we have 104.167 kilonewton, and this is the largest amongst the computed moment. So therefore, the maximum moment for the bridge is equal to 104.167 kilonewton meter. Okay, and this is our answer for example number 3. And that ends the discussion on moving load. If you have questions, please don't hesitate to comment it down. Please don't forget to subscribe to my channel and like this video. Thank you guys for listening, and God bless.